But now I've started, which means I can say happy Thursday. Happy end of week 12 of the semester, or nearly so. My countdown started like 3 weeks ago, so I'm well aware what week it is. So as I mentioned just a few minutes ago, but for those of you who hadn't joined yet, after trying to ineffectively talk with my hands last time, I made a couple new slides today and put them at the end of this lecture 7. So we were talking about configural invariance was the context of this. So let's do a little review and then I'll show you the new slides. So what is invariance about, broadly construed? What is the concern to be addressed by these analyses?
If the model works the same across groups or over time?
Yeah, if the model works the same way. So if we want to be more specific than that, what about the model specifically do we care about? Items. And what about the items do we care about? Even drill, keep going. The loadings, yep. The measure. Intercepts and/or thresholds. Yeah, so whether the measurement model parameters work the same way across groups or time or other person-level variables, essentially. And there's two kinds. There's measurement versus structural. Remember those vocabulary words?
Yeah.
So measurement concerns the measurement model parameters, the loadings, intercepts or thresholds, and potentially residual variances and covariances. Structural then refers to what? Gesundheit, goodness. What was that? Someone sneezed louder than your answer. What's structural invariance refer to? Factor means, that's one.
Factor variance.
Factor variances, one more. Covariances, yeah. So factor stuff, broadly construed, as opposed to item stuff. Which is a prerequisite for the other?
Color.
Of the two, of the measurement versus structural.
Measurement.
Measurement, yeah. So before we can talk about how the amount of the trait differs by groups or how the variance in the trait differs by groups, we have to make sure that it is the same trait in each group. And our method of doing that is to say at least most of the measurement model parameters are the same. Without that, we don't have a leg to stand on. So the first phase of this process of testing invariance is to estimate what is known as a configural model, which is the factor configuration, essentially, is where that word comes from. The same factor structure, roughly speaking, needs to be present and fit well in each of the groups or each of the occasions, otherwise it's game over. And so then I started trying to describe what I meant by that, and let me do a better job. So I threw in slides 35 and 36 into this lecture here. Make it big. Zoomers, I haven't shared my screen yet. Here you go. You can see that now. And make sure I'm recording. Yes, I am. That's always good to check. Okay. So this is an example of when it would be game over. Game over being an expression that is used at the end of video games, like you've died, there are no more lives or healths, points, whatever quantification of length of time is left. So in this example, I have two groups. And in theory, if you just say, well, it's a two-factor model, then that should be fine. But what makes this game over is that the factors don't mean the same thing across the two groups. Its items 1, 2, and 3 are measuring factor 1 in group A. Items 4, 5, and 6 are measuring factor 2. But in group B, factor 1 is being measured by items 1, 4, and 5, whereas factor 2 is being measured by items 2, 3, and 6. So to me, this would not make any sense to keep going, because how you would talk about like what factor 2 means across groups is different. Because it would reflect whatever 2, 3, and 6 have in common as opposed to 4, 5, and 6. And it doesn't make any sense once we get to the point of actually putting parameter constraints on the loadings, intercepts, and so forth, to ask if the loading for item 2 is the same, because the loading for item 2 refers to factor 1 in this group, but factor 2 in that group. So they could be different for that reason alone. So if you don't have the same type of factor structure, then it doesn't make sense to ask whether the factors are measured the same way across groups, because they're not measured the same, period. So it wouldn't make sense. Now here's when it could make sense. And Chen Chen, this is for you. This is what I was trying to describe with my hands. She's working with 4 factors at 4 occasions here. So this is where you could make it work. And the problem in this situation is that group A has 2 factors, as indicated by a covariance between them less than 1, and given that these factor variances are 1, this is the same as a correlation. In group B, we still have the same pattern, except that, let's say the analyst found that the covariance was not different than 1, so basically these collapsed onto 1 factor. If you let it stay 2 factors in group B, and at every step initially the covariance is estimated differently across groups, then this could work. So the difference between a covariance less than 1 versus 1 is not a measurement invariance problem. That's a structural invariance problem. So this is where you could make it work even though it's a 1-factor model versus 2, because you can allow essentially the 2 factors to be perfectly related and set them up in the same way. However, if the correlation really does collapse onto 1, you may have to force it to be 1 or otherwise put a constraint in to keep it from going out of bounds. So what is the magic error message that you see if something goes out of bounds? Abbreviated NPD.
Non-positive something?
Non-positive something. What's the D stand for? It's a math term. One of the few I know. It refers to, I think, the invertibility of the matrix, maybe? Does that help? Maybe, but it's not the word I want. It might be a synonym. Who knows, right? It's definite, non-positive definite, or semi-positive definite, non-positive definite. Non-positive definite means something went out of bounds and it's broken. A negative variance, a correlation above 1, a standardized loading above 1 in a model without cross-loadings. If that happens, you can't keep your model because it's settled onto a solution that is not admissible. You can't have correlations above 1. So if you let this thing try to estimate and it goes out of bounds, you may have to put a constraint on it that says, nope, top it at 1, don't let it go out of bounds to make this work. Non-positive definite is one of the error messages that is easy to scroll past. But you would know about it if you looked at your standardized solution. So the standardized solution will tell you when things go out of bounds relative to the boundaries of 1 or negative 1 that everything is supposed to be within. Okay, does this help try to describe what I was gesturing with? Mm-hmm. Like you can have different numbers of factors if there's a way that you can sort of phrase it that they look the same. But if the factors themselves are defined differently, then it doesn't make any sense to go forward. Okay, Zoomers, any questions from you on this? Now that I'm screen sharing with you? All right, so then let me escape this for a minute here, back up to where we were. So vocabulary here, configural invariance model. We started working through just a sort of a hypothetical example, and then I'll show you some real examples as promised. So let me start on slide 11 here. Configural invariance model. So my story here is 6 indicators measuring 2 factors, 3 apiece, simple structure, meaning each item loads only on 1 factor or the other, no error covariances, no cross-loadings. So my total degrees of freedom is whatever it would be per group, number of item means, variances, and covariances, we're back in CFA world, by the way, times the number of groups. So if I have 6 indicators, that's 6 times 6 plus 1, parenthesis, divided by 2 plus 6, which works out to be 27, times 2 is 54. So that's as many parameters as I could potentially spend. To estimate this configural invariance model in front of me, I spent 38. Where did those come from? 12 intercepts, 1 for each item in each group. 12 error variances, 1 for each item in each group. 12 loadings, 1 for each item in each group. 0 factor variances at this point because they're constrained all to 1 for identification, given that I've estimated all the loadings. Likewise, 0 factor means because they're all constrained to 0 because I estimated all the intercepts. So remembering those ties is going to help you in this unit. Loadings and factor variances go together. Intercepts and means go together. There are also 2 factor covariances between 1 and 2 for each group. So that leaves 16 left over. So in terms of like what the output would say, the model degrees of freedom that the chi-square test of whether you're worse than perfect, that would be 16 because that's what's left. But what you've spent, the number of free parameters is how it's labeled, which is kind of a bad name, but think of them as like free to be not 0. Free to be some number, there'd be 38. Okay. Now, in this setup here, I have it so that the factor is easily interpretable in a z-score metric. This also facilitates the next step, which is going to be what? Do you remember the next one, what it's called? Starts with an M.
Metric invariance.
Metric, otherwise known as, there's another set of words that goes with this.
Weak.
Weak, yeah. I did not make this up, but these are classical terms. And what did I tell you about how to write this up? Parentheses behind those words that say, what is it that you just held equal? Metric invariance, i.e. weak invariance in which all loadings are constrained equal across groups. Like throw your reader that life jacket. Because otherwise it'd be like, oh crap, I remember hearing the word metric in my SEM class like 10 years ago, but I don't remember what it means. Help them out. So this is what it would look like then, once we get to that step 2, metric. The differences are in 2 spots. The loadings, so as given by the bold, the loading for item 1 on factor 1 is going to be set in the software to become the same loading for item 1 and factor 1 in the other group. So we're going to do this with labels. We're going to use one label for both loadings, and that will force them to be estimated together. So we'll do that for all 6 loadings. Now, what do I have to free at the same time to make this work?
Factor variances for the second group.
Yeah, factor variances in the alternative group or groups. So the way that this is to be interpreted is that the factor variances being 1 in the first group set the scale with respect to the loadings and factor variances for both groups. They are on the same metric at this point because they're held together by the loading constraints. Now, if we forget to free the factor variances, then you are making both a measurement model constraint and a structural constraint at the same time. We don't want to do that. Will you get an error message if you do that, do you think?
No.
Nope. It'll be like, okay, if that's what you want. Here you go. How would we know potentially if we did this? Check your degrees of freedom. So we should be able to predict, based on the number of items and factors, how many degrees of freedom we save. In this case, we have 6 loadings being constrained, so we should have saved 6. But we had to release the 2 factor variances in the alternative group, so now we've only saved 4. So your new model degrees of freedom should be 20 rather than 16. Otherwise, something went awry with respect to your code. So with respect to our absolute model fit, what are the 2 possibilities that could happen relative to the configural model when we fit this one? You've got 4 choices, but only 2 of them can happen. Fits significantly better, not significantly better, significantly worse, or not significantly worse. significantly worse, or, yes, worse or not worse. Those are your choices. The only one that could get better in theory is RMSEA because it penalizes per degree of freedom. So the likelihood ratio test that we would do to compare the metric model to the configural model is a worse, not worse test. All right, how are we doing so far?
Good.
Okay, so what if reviewer 2 is reading your manuscript about your measurement and variance testing and says, you can't fix the factor variances to 1, you should have used a marker item instead. Your response?
We cannot test if 1 is different than 1.
We cannot test if 1 is different than 1. That would be the take-home message of the response, but of course you would start by apologizing that you were unclear, or thanking them for the opportunity to clarify further. Your choice. But yes, well-meaning folks would, if you use a marker item, such as for item 1 here, and a marker item loading fixed to 1 would allow the factor variance to be estimated. But then, if we use the same marker item in both groups, we can't test if that loading is actually the same, because we have made it the same. So we don't want to do that. If we fix the factor variances to 1 in the reference group, the model is still identified, that identification and scale are shared across the 2 groups, and then we can test all the loadings. Oh, and the Zoomers like how I deal with reviewers. Yes, the reviewers really need to be placated. That's like the take-home message. Everything is I'm sorry or thank you, with very few exceptions. What's interesting about my materials for this particular unit is that of all the things that I teach, I get more random internet questions about this than anything else. I am not an expert on measurement and variance. I just know how to make M+ do it, but I get so many questions from people who found this stuff and are using it to try and do their own analyses. One of the questions I get most frequently is about, why didn't I use a marker item? Because you can't test if 1 is equal to 1 if you use a marker item, is the answer. Okay, how are we doing? Good. So if this works, meaning if we test against the configural model and it's not worse, then that means the loadings are the same across groups. Broadly speaking, that means it's the same factor. Most people would consider this the most important part. I've only seen that happen a few times, though. What is more likely to happen is that the result is significant, meaning you did make it worse, and then the next step is to figure out why. This is where the modification indices are very helpful, because they will tell you, for the constraints that you placed, what the change in model fit would be if you released it. So I'm using these in a different way than as the cheat codes to improve fit. I'm not looking at any model modification indices with respect to the original model. I'm only looking at those that have to do with the equality constraints I put on in particular, because those will tell you which loading made it worse or which loadings made it worse. You can go back and re-specify the model, free the problematic 1 or 1s, and then see if it's not worse again. Next up then, scalar, otherwise known as strong. This is about the intercepts. So each indicator is still allowed to have a different intercept, but we constrain the ones for each item to be equal across groups. Traditionally speaking, any item that failed metric invariance, meaning any item whose loading was different across groups, does not go through this stage. Traditionally speaking, it's like a single elimination tournament, where once an item is kicked out, it doesn't get tested any further. Doesn't mean you can't try, though. So if you don't have a lot of items, then that single elimination tournament could cause problems downstream. So it depends on what I'm doing, but sometimes I'll go ahead and constrain all of the intercepts anyway, even if the loadings are different, just to see if I can keep a couple more, because the more that you can have constrained, the stronger your argument is that you know what the factor is measuring. So at this stage, just like we had constrain the loadings, free the factor variance, it's constrain the intercepts, free the factor means in the other group. So it would look like this on slide 16. Now what has changed is in bold in the first column for each equation, the intercepts for each are held equal. So we should have saved 6 intercepts, but then we have to free the factor means in the alternative group for a net change of degrees of freedom of 4 as well. So this is also a point of potential confusion, and this is the reason, by the way, that when anyone said an item mean is a parameter earlier in the course, I immediately said, no, it's an intercept, because I was waiting for this moment. What's the difference between a mean and an intercept? In terminology, when do we say something's an intercept versus a mean?
One is observed, the other is predicted?
Yes, if it's predicted, then it's the intercept, because it's the expected value when the x's are 0, as opposed to just expected value, period, which is mean. So this makes complete sense if you think of these as intercepts, because they are expected item responses for somebody with a trait score of 0 specifically. This seems unreasonable if you think of these as item means instead. Because we're not saying that the groups can't differ in their item responses. We're not saying that. We're saying conditional on a trait level of 0, they can't differ. So here's a picture. On slide 17 here, we have 4 possibilities with respect to each item, and either achieving metric invariance or not, and achieving scalar invariance or not, where metric is the slope, the loading, and scalar is the intercept. And the textbook author uses squiggle 1 for the latent factor, which I have just labeled as latent factor here on the x-axis. So in panel A here, this item would have passed both metric and scalar invariance because the slope is pretty much the same between groups. And at this midpoint of factor score, we're back to CFA. At the midpoint of the factor here, where 0 would be, the expected response is basically the same. In contrast, B would be an item that has the same slope, but a different expected response at that point. And in C, we have an item that fails metric invariance. And I have yes scalar here in the sense that they could have the same intercept, but it depends on where 0 is. So if the latent factor 0 were like here, that might be close enough to say it's equivalent. If it's out here, it's not. Because if they have different slopes, those slopes will eventually intersect. And you can have intercept differences just because you have different slopes. So that's the rationale for kicking that item out of the testing if the slopes differ. If the intercepts differ also, we don't know if it's because of the slopes or because of something else. So you can always try to keep the intercepts the same, but if they're not the same, it's hard to conclude why. And then you can have both like this. So ultimately what we want to be able to say with the scalar stage is that the reason why the item means may have been higher in group B than group A is because they have more of the factor, and that's why. So once we control for having more of the factor, the conditional item mean response for anybody with a factor score of 0 should be irrespective of what group you're in. If group predicts item response above and beyond the factor, that's scalar non-invariance / diff. Diff will be what it's called next week. Just trying to plant the seed, though. Okay, how are we doing? Good enough? And so just like the other process, likelihood ratio test, worse not worse, If it's worse, we got to figure out why. Look for which constraints on the intercepts are problematic, would increase model fit if they were released. Try to release those, fit it again, see if it's okay. And if at least partial scalar invariance holds, what we would conclude is that the factor is responsible for the mean differences observed in the item responses. Any item that does not pass this stage, whose intercepts need to differ, then there's something else besides the factor that is causing differences in the item, and that something else is related to what group they're in. Next is residual variance, invariance. This one doesn't have another name besides strict. So it goes weak, strong, strict. Metric, scalar, residuals. This one is of debatable importance because the conclusion that we would make is the amount of variance due to not the factor is the same, which, okay, like that could be good, that could be bad. This is the part at which if that is holds, then you can say that the measurement models have equal reliability. Only if the factor variances are the same. So we're heading in that direction as the next step. This is the last step of measurement invariance. And that would look like this. So at this step, it would be a change of degrees of freedom of just 6 in this example, because there's nothing we have to free. So there's no factor level something that goes along with placing these constraints. So just to recap, when we fix the loadings, we free the factor variances in the alternative group. When we fix the intercepts, we free the factor means in the alternative group. When we fix the residual variances, that's it. Then we get into structural invariance after that, which is factor variances, covariances, and means. And as it states in bold here, it is not a problem if we fail any of these steps, because at this point we would interpret those as real substantive conclusions. The items relate to the trait in the same way across groups or time. These are real differences in the trait that we would care about and want to predict, explain, etc. Okay, how are we doing? Reasonably enough? Reasonably good, I should say. So here's the summary then. Measurement invariance constrains, Measurement invariance refers to constraints on each of the measurement model parameters. Structural invariance refers to factor parameters instead. Want to see an example? Yeah. Question from the Zoomers, so we cannot skip any of these steps right. I don't think you should. I think there are folks who have argued that you could because it was useful for them to give the story that they wanted, but I do not think that you should. Back in the day, it used to be that the factor model did not really have intercepts in it. Basically, the programs would mean center everything. And so that step would be skipped like in the 80s. But nowadays, we put the intercepts in the model. We can talk about factor mean differences. And to me, they're part of the story. I would want to know if the mean differences are there in my factor in addition to variance differences. So according to me, no, we don't skip anything.
Follow-up question is that,
Yeah.
do they necessarily have to be in order too? It seems like it follows that lineage, but.
So this is one of those, I'm not sure if this is just the way everyone does it or if this is the way that it has to be. The factor loading and residual variance tie, to me, makes sense because one of the reasons why you could have like more or less residual variance is because you have more or less of a loading, because they're sort of compensatory in predicting the total variance of the item. Likewise, the intercept and loading, I can see why those would go together because the intercept can differ if the slopes differ, just because the slopes differ. So I think from that perspective, they go in this order. But from the perspective of, well, does that mean that you have to kick an item out if it fails the first stage and not test the others? I wouldn't necessarily say that. Like, if it works out that the intercept is the same, even if the loading is different, then keeping it the same gives you a stronger basis for inference later on. It's just that if it were to fail, you wouldn't know if it's because of the slopes or because of some other thing.
I see. So then do you just go through all the steps and then assess and then kind of go back through and kick out an item from there instead of
in the first example that I have, or is it the second? I'm sorry, I've been working on these examples all week, and so the one that I was working on this morning is not the one you're about to see. The one that I'm working on this morning, I did not follow the single elimination rule. I went ahead and kept the item parameters in because I only had 7 items, and I didn't want to like just start kicking stuff out if I didn't have to. But I think you would want to be internally consistent in how you proceed, whether to automatically kick out an item out of this process or not. I wouldn't like mix and match those decisions.
Great. Okay, thank you for the clarification.
Sure. Okay, that's all I think that was all I was going to say about that. I wanted to show you the example. This is example 7a. I have this one in R, and this is one of the few in which R cooperated and gave me pretty much the same answers. Not at all steps, but most of them. So I did go through and make the R code that goes with this, as well as the full output. And then on the class website, there's a link to Jonathan's version of this where he has the full R markdown of everything if you want to look at that as well. So I'm going to tell you that this is the textbook example, and I am almost positive these are fake data. Do you know how I know that? Because we're testing invariance across men and women, which magically have exactly the same number of people. We're doing it on a 9-point Likert scale, which I've never seen in real life. And because everything works perfectly, except it actually doesn't. So I found something different in the same data than the author did. And so my results differ from his with respect to scalar invariance. But so this is like the ideal situation of equal groups, large enough groups, items that are normal and continuous enough for a CFA to be a reasonable thing. So this is a measure of depression, 9 different symptoms of depression, and then each person is providing a response as to how much this affects them, essentially, where more is worse. So this is a trait where higher scores mean more depression. I have a disclaimer here that what I'm about to show you is way more code than what you technically have to do. In efforts of helping analysts do this more efficiently, both Mplus and Lavon have a set of shortcuts where you can just say fit metric, fit scalar, and show me what happened. I am not showing you that because I want to focus on what is happening to the model at each of these steps. What gets freed, what gets fixed. And those automatic routines also don't have much to help you when it fails. Like if it's worse, you want to do something about it. You don't just want to be like, okay, I guess I have to take my ball and go home. Like you want to go for partial invariance, and they don't help you. So this is more code, but it's more transparent and potentially more flexible. So I stand by my decision to give you a whole bunch of code, even though there are easier ways to do this. So this is Mplus that we're focusing on here. Do I have, I don't think I put anything with respect to the R syntax, but let me pull it up. Nope, that's not what I want. Oh, 1 second here. So I can show you a little bit, just insert 1 second here. Actually, here's what I'll do. I'll point you towards the example that Jonathan made in like 2017 or whenever it was. So this is for our class, week 12. Here's the full Lavon version. That'll make it easier so I can blow it up. So I can show you briefly how the code looks like in Lavon to go with this too. Okay. So the same code to input everything with respect to the data and what output options to turn on apply this whole time. So it's only going to be shown once. As usual, you can have just the variable, the dataset name if it's within the same folder as your input file. Otherwise, you may need to print the whole path. And I apologize for how difficult it is to use Mplus for some of you on the virtual desktop. If it throws an error at you like error number 9, or if it throws an error with respect to going over 255 characters, the solution is to move your analysis to the university's H drive. That is a much shorter path, And the virtual desktop seems to understand that access point much more easily across packages. So that's what I would do first. If that doesn't work, you may have to put the path to your H drive in here, like, you know, this kind of thing. And if that still doesn't work, let me know. Hopefully that will eliminate most of the points of brokenness for working with this. In terms of new pieces of code, this is the new line. Grouping equals. Tell it which variable in your data set is going to, you want to have separate models estimated for. And then you can put the labels in there so that it uses the labels in the output. Highly recommend, because you don't want to be looking back at your files 3 years from now and be like, who is group 0? Have the words. That will make your life easier. Otherwise, we're using MLR because we're back in CFA land. I'm using modification indices, and this 3.84, that means only show me modification indices that would improve model fit significantly at the alpha of 0.05 for 1 degree of freedom. So that's the critical chi-square cutoff for that likelihood ratio test result. And I'm asking for standardized solution and the residual output for completeness, but we're not going to pay attention to those because all of these invariance constraints happen on the unstandardized parameters, not the standardized. In each of the models below, the model for the reference group, its code, is going to stay exactly the same. What changes in the code is what we're saying should happen for the alternative group as a comparison. There are several different ways of specifying multiple group models, and I have gone with a strategy that is the most typing but the most transparent. Inside the M+ user manual, they have a whole chapter about multiple group models and the various ways you can set them up. If you need to do something that is different than this, like if some items are only measured in some groups, then the model has to be set up differently for that situation. So this example, it's the same 9 items for both groups. So we have the regular blue model part, but then we have a separate model min. And it doesn't turn blue. But it essentially means, what would you like the other group's model to look like? And then you write the same things here. So our configural model here has depress is the name of my latent factor, measured by items 1 to 9. The star here is necessary because by default, the first item's loading is fixed to 1. The star overrides that default for all 9 of them. I have the parameters on the women model here as the reference group labeled, but they're not constraints yet. They're just labels. So I have loadings 1 to 9. Inside the brackets are where I refer to my variable intercepts, 1 to 9. So I for intercept, E for error variance, 1 to 9. And this particular data set had a covariance between items 1 and 2's residuals that earlier in the chapter they had figured out they needed, so that's there as well. Items 1 and 2 are depressed mood and loss of interest in usual activities. So I'm not going to pretend to be a clinician who interprets that as meaningful, but I'll just take their word for it. Like I said, pretty sure these data are fake. To identify the model, my factor variance for depression is fixed to 1. My factor mean is fixed to 0. What would happen if I switch these? A semicolon isn't really used in this situation. You want to bet? You know what happens if I forget that? M+ will be mad at me. What if I do this instead? It's an easy mistake to make. What will I get back? An error message. Because I will have just fixed the factor variance to 1, which means it can't predict the loadings because it's a constant. So make sure that the outside the parenthesis is at 1, inside the brackets is 0, outside of it is 1. The model for the men looks exactly the same, except there's no labels, because the labels are going to be selectively applied to become constraints. Okay, with me so far? in Lavon, and again, I have this inside the download packet, but this is the Jonathan's version. Even more typing. So in front of each item where the loadings would be, there's this. So it's writing two different labels for the same parameter to go across the two groups. And he has an F because in his example it's female, whereas I switched it to women, but it's the same idea. So as long as this, as long as this is different than this, you'll get two different answers back. Can you guess what's going to happen once we want to make them the same? Make it the same word in both places, and then they have to share. So the labels go next to each of the items in the Lavon syntax, whereas they go at the end of the line before the semicolon in this syntax. So here's my results. 56 free parameters, meaning things estimated, in this model. Let's count them up. Where did the 56 come from? How many items do I have?
6.
9 this time. Yep, there was 6 in my example, because I ran out of room on the slides to make 9, so that's why it's 6. And there's only one factor in this example, too. This is the simplest example we're going to see. So where does the 56 come from? How many parameters does each item have?
3.
Yeah, each item. 3 times 9 items is the 27, times 2 groups is the 56. Or yeah. Oh, 54. Where are the other 2 that I missed? No, not factor stuff. These are all fixed.
The covariance.
Yeah, this one.
Yeah.
2 residual covariances. That's the extra 2. Yep. So this is not just a pedagogical tool. I do this when I fit models. I try to figure out like how many there should be and see if it matches. And if the number doesn't match, I know there's a problem in my code. Which is my model, HO or H1?
HO.
HO, we are always the hoe. The HO scaling factor for MLR is pretty close to 1. Another reason I know these data are fake, because you would not normally expect perfect multivariate normality out of depression symptoms. In terms of fit, here's the chi-square tested model fit. What's that one telling us?
The comparison between the HO and H1.
Yep. So this 94 is a rescaled likelihood ratio test between my model against the perfect saturated model. The fact that it's significant means that it's worse than perfect. However, it also breaks down how much of that chi-square came from each of our groups. Now keep in mind that the group with more people contributes more to the chi-square. So these numbers are only directly interpretable as some kind of like misfit if it's exactly the same. What about the other fit indices? What do they say? RMSEA, CFI, TLI. Meh. It's okay. It's pretty good. RMSEA has 0.047. We want that to be under 0.05, 0.06-ish. This p-value here tells us that it's not different than 0.05. That's good. It's actually under it. How about these two? What makes them different? CFI, TLI.
With respect to the null model, ours is better.
Yeah, how much better we are than the worst model. The null model has means and variances and no covariance. So it's a different standard of comparison, which is why you can come to different conclusions based on looking at these different fit indices. But these are okay. So I have this figure here, which I made in Excel, of course, as foreshadowing. What this is a depiction of the factor loadings across men and women, in red and blue respectively, across the 9 items. So this can help us try to anticipate like where we might find differences in terms of which ones look disproportionate. Not always visually possible to see, but this is just my way of trying to make a picture that would go with this sort of idea. So here are the unstandardized results. The left-hand side is the results for the women as the reference group. The right-hand side is the results for the men. Even though each group has a factor mean of 0 and a factor variance of 1, they are not on the same scale. It's like they're standardized within group to have a mean of 0 and a variance of 1. So we can't make any conclusions like about the relative amounts of these because they're not on the same scale. The purpose of estimating this model is just to verify that a single factor model fits in the first place. All right. Next up then, metric invariance. So the change in the code that makes this a metric invariance model occurs only on the right side here. The reference model code stays exactly the same the whole time here. It's the men as the alternative group model that changes. And I'll highlight the changes right here, right there. So I have added the same labels that are being used for the women to the men's factor loadings. So it's L1 to L9 over here, and I just added L1 to L9 for the men as well. That means they're not just labels, they're constraints. So L1 is what I have called the factor loading for item 1 in each group at the same time. That means it has to become only one number, not two numbers. Same with L2, L3, L4, all the way up to L9. Then down here, the factor variance in the alternative group is now estimated. So I've removed the @1 that was there before, and I put a star in its place. The star is just for emphasis. You don't actually have to type it, but I'm making a point. So those are the two changes. Loading constraints via labels that match across the two groups, and free factor variance in the alternative group. The factor means have to stay at 0. The factor intercepts are all separate. So this model is halfway linked across groups. The factor loadings and the factor variances have a shared scale that is set by the reference group factor variance of 1, but the means and intercepts are on a different scale so far. In lavaan code, at this point, the factor loadings have the same label. So L1, L1 for the first item, L2, L2 for the second item, and so forth. So same exact idea, just a little bit different in terms of its instantiation. Okay, ready to see what happens? So our HO then, we want to not compare against H1. The goal of this is to compare this HO against the previous one. So I did that via I have a spreadsheet for likelihood ratio tests in lavaan. You can do that with an ANOVA function. And so here's the result. It looks like the loadings are, the loading constraints, 8 degrees of freedom. Why is it 8 to not 9? Because there's 9 items. I have 9 loadings that I've constrained. Why is degrees of freedom for the difference only 8?
Because the factor variance is being estimated.
Yeah, we lost 1 for the factor variance being estimated. But non-significant p-value and really non-significant. So does the model fit get significantly worse than configural? No, it does not. Is this good news or bad news?
Good.
It's good news if we want to say that depression is being measured in the same way in men and women. So in other words, whatever differences between men and women we had in the loadings are largely attributed to differences in factor variance. Now it's not exact, but it's approximate. So now we can look at the difference in factor variance across groups, which is on page 4. So depression is a variance of 1 in the reference group, which is women. Depression has a variance of 0.86 in the men group. So men are less variable from each other in their depression trait relative to women. If men were more variable than women, then the factor variance would have been estimated as some number larger than 1 instead. So everything is relative to 1 as an anchor point, as the key of this model, so to speak. I checked the modification indices. They didn't say any of the loadings were individually problematic, which makes sense since the overall chi-square difference was only 4. So there's not much room for misfit there, so that looks like all the loadings are the same. Hooray. Next up, what comes after metric? Scalar. So we cleared the hurdle of weak invariance. Now we're looking for strong. Yeah, strong / scalar. And I have this labeled as 3A as opposed to 3. That's foreshadowing what's going to happen. So we got to find the differences in the code relative to the previous model. It's right here and here. We have the same labels applied to the intercepts across groups now. That means we're constraining them to be equal. And because we have constrained the intercepts to be equal, we want to release the factor variance, or excuse me, factor mean, keep the factor variance released as well. So how many degrees of freedom should we have saved if we did this correctly?
8.
Another 8, because it's 9 intercepts minus 1 factor mean we gave back. Net change of 8. So if I test the overall change in fit, I get a chi-square value of a rescaled likelihood ratio test of 12-ish with a p-value of 0.13. Now at this point in your textbook, the author says, cool, moving on. And I say, well, wait a minute here. So if I look at the modification indices, I found something interesting. So this section of the output here, which is at the very end, hey, stop that, of the M plus output. So the columns here, MI is modification index, stands for by how much would your chi-square go down if you added this to your model. The EPC is the expected parameter change, and the standardized version of that is the last column. So 5.9 roughly is the change that we would see if we let item 7 be different between groups for its intercept. So the old constrained item 7 across groups was decided to be 3.711. That's what it came up with as the shared intercept between groups. So what this is saying is that if we let that be different, the one for women would be higher by 0.158. The one for men would be lower by minus 0.219. So this is what it wants to be. So this is a point at which reasonable people may disagree with me, but here's my logic. Of the total change, or is it? It is on the same slide, thank goodness. The total amount of misfit that we introduced by constraining the intercepts was a chi-square of 12. That was across 9 items. Half of that misfit was due to one item all by itself. To me, that's salient. Now, if I look at the content of the item, what is item 7 about? Feelings of worthlessness or guilt. So what this analysis is saying is that it looks like women in this group have a higher expected response to feeling worthless or guilty than men do, conditional on a trait level of 0. So there's gender differences in the expected response above and beyond the amount of depression. So based on the fact that half of the model misfit was attributable to one of the 9 items, I'm letting it free, letting it go. So the constrained model then, where both item 7 intercepts were 3.7, creates a factor mean for the men of minus 0.11, meaning they're a little bit lower than women. And this minus 0.11 only has meaning relative to the factor mean of 0 in the reference group. So what these numbers actually are is entirely based on your scaling. Like if you had said the factor mean should be 10 in the reference group, then this would have to adapt to that. So like 1/10 of a standard deviation, roughly, something like that, lower on average. So if I fit the partial scalar model, so partial means some of this parameter are constrained, but not all. Here's how I did it. This right there. I made a different label in the men than I had in the women. So in the women, it's just I7. In the men, it's I7M. Can you guess why it's M? For men, yeah. I'm throwing myself, this is again, the life jacket from my code 3 years from now. Like, what is this? What's the M for? Oh, yeah. You can pick whatever label you want, but picking something that makes sense will help you in the future. So now there's 2 potential hypothesis tests that I might want to do. I can see if it's not worse still, or yet, and I can also see if I headed in the right direction. So relative to the HOs, the first thing that I did is, am I headed in the right direction? Relative to the model in which all intercepts are shared across groups, does fit get better if I let item 7 go? If I add a parameter back in? Yes, it does. If I compare this new model where everything is invariant except item 7 to the model previous to it, the metric model, then that's my likelihood ratio test for scalar partial invariance. So there's no more modification indices at that point, so I decided this is good enough. In terms of the new output, I have 3 things here highlighted. This is what the intercept is in women. This is what it became in men. And then here's what the mean difference is in men. So by letting item 7 differ, the group difference in the factor mean changed. The way that I would interpret this now is that the depression factor is responsible for the fact that men have lower means to all of their items, except 7. 7 goes the other way. In 7, women have the higher mean. So something else that is related to gender is predicting differences in the expected item response. So now there's 2 different potential, what's the word I want? I'm running out of English again. 2 different potential pathways one could go down at this point. Let's say that your ultimate goal of this analysis is to examine how depression relates to X, Y, and Z other stuff, and whether depression relates to this other stuff differently in men and women. That would be like a moderation kind of model. Now, can I still answer that question, given what I found so far? 9 out of 9 loadings were the same. 8 out of 9 intercepts were the same. I say, yeah, it's mostly the same trait. But what do I want to do with item 7? I could leave it and just let it be different. I could let each group have a different intercept and be like, yep, something else besides factor mean differences in depression is causing differences in the group response to these items. Cool, fine with me. Let it be different. Or, nope, that item has diff, it's gone. Either one of those could potentially be problematic. nope, it's gone, is the easiest way to deal with non-invariance. But I would have to make sure that in terms of the construct validity, right, the content of the items, that I'm not losing anything by deleting feelings of worthlessness and guilt. Is there any other item that sort of captures that? Not really. So I could get rid of the item, and then I would say that I have full invariance, but potentially miss part of what I want to measure. Or I could just let it be different and accept the fact that men and women respond differently to that item for reasons that have nothing to do with depression. I don't think there's a right answer here. I think it depends on your arguments, what you want to do, what the precedents are in your literature area, and so forth. But knowing that you have these choices is important. Just adding up the items, you would never know this. What you might do in the context of a high-stakes test result is very different than what you might do in the context of research. Thoughts, comments, questions? No? No thoughts, no comments, no questions? 3:05.
Flawless analysis.
Yeah, flawless.
No question.
I know. Well, that's what happens when you make up the data. Everything works perfectly. That's why I have 3 more examples where everything falls apart on you, because that's what happens in real life. The letters here. So I have a convention when I'm doing these models where I use a number to describe like the level of invariance and then a letter to be like keep track of the iterations. So like in the example that I was building this morning, it's like metric A, metric B, metric C, and then we get to scalar A, scalar B, scalar C. I swear to God, this happened in once upon a time when I used to do projects in this class and people were doing these analyses. Like I had a student come up to me and she's like, I'm at scalar R. It's like, what? Like, yeah, that happened. Like, I'm at scalar R. How long do I have to keep doing this? Okay, you don't have invariance. Like, you're done, right? If you get to scalar R, like something like that's not a project that you can save, I think. And in her case, it was actually invariance across children of different ages. And it was about their feelings of self-efficacy, about how well they could do math. And I didn't really get that until I became a parent, right? Like if you ask a 5-year-old how great they are at math, I'm excellent. 5-year-olds are excellent at everything. Just ask them, right? I wish I had the confidence of a 5-year-old. But like as you get older and you start to see like yourself relative to your peers, then maybe your opinion either changes or gets more realistic. I'm not sure which. But the way that these items were working was completely different across kids of different ages. So I was like, scalar R, you're done. Like there's no saving that. But that is one of the potential criticisms, though, of this kind of approach is like every time you go into the well and you take the modification index and it's like, okay, I'll try this one. Doesn't fit yet? Okay, I'll try this one. Doesn't fit yet? Like you would come down to a completely different set of answers potentially, depending on like what order you freed things in. So there's no real good answer to that. There's a lot of research on invariance testing and diff and how to best do it, but there's not necessarily one solution that's going to work. But if someone criticizes this as being like subject to type 1 error or sample fluctuations, yes, I agree. Ideally, you try a couple different methods, and if they land on the same solution, then maybe you have more faith in what you found. But it does get complicated, for sure, because any constraint, like you can't free everything at once. It's not identified. So you've got to lock some things down to test others, and what you lock down has a consequence for what you then find with the others. It's like trying to hang on to a bar of soap that's already wet. Like it's just, you grab at it and you just, it's going to fall. Dry soap is much easier to handle. So, scalar B, partial scalar invariance was okay. Then we did residual variance invariance. Since we have just a few minutes left, I'll wrap this up. Residual variances then, here is the one change. This is page 9. Note that I kicked item 7 out of the tournament. Because it had failed scalar, following the typical practice, I did not test residual variance invariance for it. I could have, but I didn't. So now we should have a change of 8 degrees of freedom. And this is especially how I know these data are made up. This never happens to residual variance invariance. The amount of not the factor is the same across groups for all items except 7. Men feel less worthless and guilty than women do still, and men are less depressed than women a little bit. Then we get into the residual covariance. So this one and this one share a new label. That one made the model worse, p less than 0.05, so we're just going to leave that separate. Factor variance is the last one, second to last one, structural invariance test now at this point. So this one, to test factor variance invariance, I fix the variance back to 1 again, because it's already 1 in the reference group. So 1 is equal to 1. So this is an instance in which you don't do it with a label, you do it with a value. So we're fixing both factor variances back to 1 again. Model's not significantly worse. In the solution, the factor means are still allowed to differ. The mean in men is estimated as lower by 0.094 with a Wald test p-value of 0.27. So what does that mean? What would I conclude based on this little piece right there? Non-significant? Looks like the mean differences between groups are not significant according to this. Turns out that's all you need to do. Because if I go through and formally test the mean invariance by fixing the mean back to 0 again, I'm on page 14. The p-value that I get from that likelihood ratio test comparison is pretty much the exact same. So you don't really need a likelihood ratio test for the last result, because the factor mean being tested against 0 is what the Wald test is already doing. All done, and as promised, here's some words. How long the words would be would depend on whether this was the point of your paper or this was just a side thing that you had to do on your way to making it a point. This write-up this is what a results section would look like if the point of the paper was to report the invariance results. If the point of the paper was not, all of that would go in a supplement, and I would have like this much in the paper. Just what happened. Invariance was tested following the procedures of blah, blah. Here's what happened. For details, see the online supplemental materials. Ta-da! We made it. So, classic textbook example, everything's invariant. Next week, we'll get to see things start to fall apart. But not get to scalar R. It's not that bad. I think I'm at scalar E or F is the highest one. It happens. Any questions, comments, or otherwise before we call it a week? Not just a day. No? Yes?
Sorry, but what is the meaning of the A's and B's? in
The A's and B's?
Table 1.
Table 1.
At the end? Yeah,
Yes.
sorry. Yeah, at the end you have a table.
Mm-hmm.
Yeah, that one. Sorry, but what's the meaning of those A's and B's?
So my system of trying to keep track of these models is the number refers to like the level of the model and what's being tested. So like scalar is 3, and metric is 2, and configural is 1. And then A, B, C is like how many parameters are being constrained. Where B is like I let 1 go, C is I let 2 go, D, like that's why if you had to keep releasing one at a one, like you could get all the way through the alphabet if you had enough parameters.
Okay.
That's why my student said she was at scalar R, and I was like, you just need to stop. Like this is, invariance is not in your future. So that's my convention. You can follow it or invent your own. But. All right, then I will see everyone next week. Let me know if you need anything. Homework is due on Monday. Homework 3 and 4.